Okay, so we're over here in Unity, and I've decided I'm going to actually just make a duplicate copy of this because I still want the old logic to be able to work if I want to test it out. So I'll make a duplicate of my server player, and we're just going to rename him predictive server player, and just get rid of the 1 on the end of him. We're going to remove our network transform because we're going to be doing that inside of our server movement script. And I'm also going to make a copy of our server movement script. So in server auth, I'll just Control D to duplicate that. We'll rename this predictive server movement and get rid of the 1. And then I will open that up in Unity, and we'll just call this predictive server movement and save that. That should get rid of all of my errors. Jump back into Unity and let it render. I've got my predictive player here. I'm going to add my predictive server movement script and then copy these values across. So we've got 60, we've got our player transform. Just open up the prefab here. My player transform is my player transform, and my character controller is also on this, and that is all that we need for this. Everything else is set fine. So we will hit save, and I will back out of that now, and then we'll just remove our original one that we had here. So get rid of our server player movement. All this does is means that if you ever wanted to use the network transform method, you can just use the existing network transform one, and we'll make updates to our predictive one. So for starters, we're going to need to introduce the concept of a tick, and that is going to be done just as a integer. So I will call that private tick, and we'll start that at a value of 0. We're going to have a tick rate, which is a private float called tick rate, which is going to be equal to 1f minus 60f. So that's effectively 60 FPS. Then we're going to have another private float that we'll call tick delta time. Now this is going to act as a value that stores our delta time, and we're going to add and subtract to this value to get down to when we actually are at the next tick. Because we're going to be handling our own ticks, we want to be able to store a certain number of them on the client side and then be able to check them on the server side. So we're going to need to create a buffer for that. So I'll call this a private const int buffer, and we'll just set it to 1024. I believe 1024 is the equivalent of 16 seconds worth, or 17 seconds that would be storing on the client side. And this is good for you to be able to store historical movements so that you can roll back at a later point when we do reconciliation if needed. So we'll save that, and then we'll jump back into our scripts folder in server auth, and I'm going to create a brand new script that I'm going to call handle states. And open that up. Now in handle states, I'm not going to be assigning it to any game object, so I can actually remove this mono behavior. And I think what we'll do is we basically need to have an input state, that is the current tick that we're trying to store, as well as a transform state, which is effectively a serializable reader writer of the values that we've stored in current ticks. So I'm going to put both of those classes inside of handle states. To me, it just kind of makes sense that they're related to one another. So I'll create a public class called input state. And in our input state, all that we really want to store is our tick. That's effectively going to be our ID of the movement that we've done. And then our public vector2 move input, as well as our public vector2 look around. And the reason why we want both of those is because they're the two values that we were sending to the server in the past. So we have our move input here, and then we also have our look around value here. So if you would name those different, you would be able to save them in your state differently. Now for this next class, we're going to actually need using unity.netcode, and then we're going to create a public class that I'll call transform state RW because it's going to be a reader writer, and that's effectively what's going to be responsible for packaging up and sending the network and then reading it on the other side. So we're going to be extending a iNetwork serializable, and in this class I just need to have my public int tick. I need to have my public vector3 because this is going to be the final position that the person's in. A public quaternion, that is my final rotation. A public bool that I'm going to call is moving. And the reason why we have this is moving here is because we don't want to necessarily be updating every other player all the time. We only want to update them if they've taken a move action. So we use this as a bool check to ensure other players have moved before we update them. Those are the variables we're going to need. Now we're going to need to actually use the reader writer. So I'll create a public void network serialize of type T, buffer serializer of type T that we'll call serializer, where T is an iReader writer. And in this method, we are going to basically just check if we're the reader or the writer, and then we're either going to read or we're going to write. So if the serializer dot is reader, well then what we want to do is read. So we'll say var reader equals serializer dot get fast buffer reader, and then reader dot read all the values that we've stored. So read safe out tick, we want to get the tick value, and then we want to do that for the other one. So we'll say tick, final pause, final rotation, and is moving. So we'll grab that, final pause, final rotation, and is moving. And in the scenario that we are not the reader, then we must be the writer. So we are going to start our var writer, and then we're basically just going to serialize with a get fast buffer writer this time. So create the writer, and with the writer we're just going to write the values into it. So write value safe, and then we are going to write the tick value that gets passed into it, as well as the others. So our final pause, our final rotation, as well as the is moving. Now these are our two classes. We're going to be using this inside of our server player movement, basically whenever we want to create a new tick. So whenever we want to track some movement, we're going to package it up inside of this input state, and then we're going to pass it into our reader writer, and we're going to say, hey, I want you to read this if it's coming back to me from the server, or I want you to write this from the client side and pass it over to the server. Now we're going to jump back over to our predictive server movement, and I'm going to create instances of those. So we've got a private handle states dot input state, and we want a array of this, and we're going to call that input states. So effectively what we want to do is we want to be able to store up to the amount of input states that we have in our buffer. So we're going to say that that is going to be equal to a new handle states dot input state and the size of our buffer. So we'll be able to store up to 1024 input states, and then we're going to do the same with our transform state. So I might just copy this here, and instead of having our input state, we're going to have our transform state read write, and the same over here, our transform state read write, and we'll call that transform states. Now lastly, we're going to create a public network variable, because we're going to have to send that transform state over to the server, and we need that to be a value that's tracked across the network. So we've got a network variable transfer state. We'll call that the current server transform state, and that can just be a new network variable, and a public handle states dot transform state read write that we are going to call previous transform state. Now the reason why we've created these two here is so that we have the potential to roll back in the future. We're going to assign these states now, but we aren't going to look at doing any kind of reconciliation in this tutorial. So we are going to use that in some event-driven changes. So I'm going to create a private void on server state changed. And in there, I want to take a transform handle states dot transform rw, which is going to be my previous value, and my handle states dot transform rw, that is going to be my new value. And effectively all this method is going to do is it's going to say my previous transform state is equal to my previous value. And then we're going to subscribe to that method. So private void on enable, and in on enable, I'm going to say current server transform state dot on value changed plus equals on server state changed. Okay, now that we have that, let's take a look at our update and just understand what it was doing at a high level. So firstly, we were checking to see if we were the server and the local player, and if we were the server, then we were allowing ourselves to move instantly on the server. And if we weren't and we were the player, then we were requesting to move. Now we never actually had any logic to update players that weren't us, because the server had the network transform and the network transform handled that for us. So it would update and just update us even though we didn't have any code to do that. So now that we've got rid of the network transform, we're effectively going to have a move ourself if we're the server and the local player, move ourself if we're the client and the local player, and then also a simulate everyone else on the network movement. So I'm going to wrap these two methods here into one local player movement, and then we're going to create a simulate movement to get everyone else's movement on the server. So we'll start off by creating a method that I will call public void process local player movement. And remember, this is going to do the movement on the server and the client. So we're going to need to pass in our information. So we've got a move input as well as a vector2 of our look around. Okay, so this is the part where we're actually going to implement our tick delta time. So I'm going to say tick delta time plus equals time dot delta time. And I can say that if tick delta time is greater than our tick rate, then we want to go ahead and actually record an action. So in this case, I want to get a reference to the buffer index that I'm up to. So I'll say int buffer index equals tick modal buffer. And now, because this is only going to be called when we are the client and we are the local player, we don't need to check whether we're server or anything else because it's already gated in what will be in the update logic later on. So we're just able to call our RPC straight away. So I have not yet created the RPC. We'll create a move player with server tick, and remember that's going to be an RPC. And then because I'm on the client side and we're doing client predictive, I'm now able to just call move straight away. So I'll do my move at my move input, and I'll do my look around at my look around. So I'm going to be sending off the request to the server to say, hey, I want to move to here. And I'm also going to locally be doing that movement at the same time. And now we're just going to create some input states and some transform states to track where we are now. And then we're going to store that inside of our buffer history. So inside of our states history. And then we're going to reduce our tick rate and increase our tick if needed. So we're going to start off with handle states.input state, which we'll just call input state, and we'll make that a new, and in here we're going to store the current tick that we're up to, our move input, which will be our move input, and our look around, which is going to be equal to our look around value. And then we just need to store the handle states transform state, which we'll call transform state, and we'll make that a new as well. And then that's going to be also storing the tick at the tick value, as well as the final pos at our transform.position, and our final rotation at our transform.rotation. And finally is moving will just be set to true. Now we need to store both of that in our buffer that we've created up here. So this keeps track of all of our states and basically historical states. So we want to add that into our buffer. So we'll add a input states at our buffer index is going to be equal to our input state, and our transform states at our buffer index is going to be equal to our transform state. And then we just need to say tick delta time minus equals our tick rate. So we reduce our tick delta time back down. And then we say if tick is equal to the size of our buffer, because we don't want to have an overflow here, we have to then set our tick rate back to 0. You would get an overflow because obviously this is a max of 1024, and eventually you'll hit the cap on this. And we just want to basically reuse the buffer again. So we'll just say set it back to 0, otherwise tick plus plus. And now we need to create our RPC. So I'm going to uncomment this, and we will need to pass in our tick to this, our move input, and our look around, and then we're going to generate this method. And this is actually movement on the server, so it's quite straightforward. We're going to be doing the move with our move input. We're going to be doing the look around with our look around, and then we just need to store our states. So I've actually got this here already, basically. We can just say our transform state. So we're going to store on the server where we are. And then we just need to set our previous transform state to whatever the current server transform state.value is. And then we need to update our current value with the new value of our state that we're saving. So we'll say state, whoops. We'll say transform state. Okay, so this process local player movement actually now handles both the server-side requirements as well as the local client movement and stores states on both sides. Now that's great, but because we've removed our network transform off of our game object, we are no longer going to be able to see the other players get updated, and that's because the network transform basically handled sending updates back out to everyone. So we need a way to simulate the other players' movements. So we're going to create a method for that exact purpose. We'll create a public void simulate other players, and in simulate other players, there's not actually a lot we want to do that's very different to what we've already done. Ultimately, we need to limit them to the same tick rate that we're on in our method. So we're going to take this here because we need to limit them to the tick delta time that we've got as well. Except this time when they're in it, we also want to make sure they're actually moving, because there's no point updating them if they haven't actually taken an action. So we'll say if the current server transform state .value.is moving is true, that means the person is actually moving. So we want to say transform.position is equal to current server transform state.value.final pos, and then we want to do the exact same for their rotation. And we'll change them here to rotation. And now that that's done, we just need to reduce the tick delta time by the tick rate and increment our tick again. So we'll say if tick equals buffer, tick equals 0, else tick plus plus. And I'm just going to close that bracket off. And now that we've got that, we can finally start touching our update method. For starters, I'll remove our 2 old server RPCs because we've got one server RPC that does both of this now. And we're also going to delete everything that we have. Oh, actually, we'll move this out because we're going to need this. So we've got our tracking of our mouse delta as well as the tracking of our move input. And it's quite simple now because we're not checking if we're the server and the client anymore. We're just checking, are we actually the client, the local player, or are we someone else? So we're going to say if is client and is local player. Then all I want to do is go ahead and call this process local player movement that we created with the move input as well as the mouse delta value. And if we are not the client and the local player, then we must be someone else. So if we are someone else, then what we need to do is say simulate other players. And so that will update all the other players and their locations provided that they're moving, and it will keep us up to date by moving ourselves with our new method. Okay, so that's actually all the code we're going to need to write for this one. I did notice a few errors that I'd made along the way, so we'll go and fix those up now. The first one is inside of our move player with server tick RPC. I need to make this a server RPC and obviously have server RPC as to make it a call. If you don't do this, you'll get an error telling you about clients not being able to execute network variables, which is true. You wouldn't want clients to be able to do it. The second thing is that this will continually execute because I didn't have tick delta time minus equals tick rate, so it was never getting lower. And in our move, we were still operating on time.delta time. So what you would find if you ran this without changing this is that a player might on the server appear in a different location to where he is on your client if you'd been running for a long time. That especially would happen if you're running one built version versus your Unity editor, because Unity editor will run different to a built version. So we're going to change this rather than time.delta time to be our tick rate. Let's save there. And then because we've updated this name, we just need to make sure we update this name here and hit save. So that's all the bugs in the code. There was one problem I also noticed with here. Originally at the start, I took a copy of the server player instead of the server player with camera. So I'm going to delete this guy and we'll make a duplicate of our server player with camera. I will rename that predictive and we'll just set it up again. So it just needs to remove this and remove our network transform, and we'll add our predictive script. We'll give him a movement speed of, I don't know, let's say 50, a transform, a character controller, our virtual camera, and our audio listener. Let's save on that. And because we've removed that, we just need to update our network manager with our prefab as well as our network prefab. With that done, we can now build the game and test it. And now that that's built, let's open up a few instances of this. We'll make one of you the server. I'll make one of the Unity ones a client and another client. So we got our player and we got our other player. You can see they're both able to move. The server should be in the exact same alignment here with the player, the first player that joined, and we should be able to see everything exactly in position, which it looks like it is. That's quite good. And if I move you to another location, I should still be able to see you in the other location. Excellent, so now we've implemented that client predictive movement. Okay, that's it for this tutorial. In the next tutorial, we'll take a look at experimenting with a bit of ping to show that lag, as well as our reconciliation. As always, this video wouldn't be possible without the support of my patrons, so I want to give a big shout out to Pat in the Emerald tier, Raphael in the Gold tier, Lanky Moose in the Silver tier, as well as Castle Coders. Thanks everyone, and if you would like to follow me as well, it's patreon.com/Flarvain. See you guys in the next video.